on everything. And I think we'll be ready to start in a moment. Okay, so I think that, yeah, welcome on the third day of our school. The first lecturer today, again, is Roman Krems, who you know from yesterday. So Roman, the screen and internet connection is yours.
Thank you, thank you. All right, so we're gonna continue from where we were yesterday. Let me share my screen. Let me first open this full screen. And just give me a second here. So can you see my PDF and my mouse?
Yes, both.
Good, good. All right, so we're going to continue with our discussion yesterday. Before we begin, let me address some of the comments or questions that were posted, I guess, in Discord, and then Anna forwarded those to me. Thank you, Anna. So yeah, first of all, the question about the equations. I mean, I'm fully aware that I put too many equations in my presentation yesterday, and I did this intentionally. So if you didn't understand all of the derivations and all of the math that we went through, especially towards the end of the presentation yesterday, don't worry about it. The reason I put the equations in the slides is because I was hoping that Anna would forward those slides to you, and then so that you know, if you have time, you could take a look at them. And if you have any questions, you know, so I just wanted you to have the fuller derivation, mathematical derivation of what we're talking about. So if you have any questions about those equations, feel free to reach out to me by any means that you have available to you. So don't worry if I lost you somewhere. So we're going to summarize some of the main takeaway points from last, I guess, presentation today. Okay, and I'm going to try and slow down and go slower today. I guess another comment I wanted to make is, you know, if you find that I'm going too fast, or you know, yeah, if you feel like you're falling behind, please don't hesitate to interrupt me. Tell me to repeat or slow down, because you know there's no point in me doing this unless you are with me. Okay. So there's been a couple of there were a couple of interesting questions posted. I'm going to address one of them now, and then I guess some of the other questions later. So one of the questions was about the regularization. You know, Anna, I guess, asked, you know, when do we use what kind of regularization? And like I said, it's a this question requires a lengthy discussion. So I'm just going to give you one example of when people would use other than the ridge regularization. Okay, as we discussed last day, regularization comes in the form of a term that you add to the loss function. For example, when you do linear regression, you could regularize your problem either by this term here, and that would amount to what we call lasso regression, or you could regularize it by this term here, which we then call ridge regression, right? So most commonly people would use ridge regression, but a lot of times it's actually you know, which regularization to choose, you know, is determined by trial and error. But there are circumstances when you would prefer one or the other, and what I wanted to show you today is an example of where you would prefer, for example, to use lasso. And so, like, before we look at the example, let's think about the difference between the two. So what I'm talking about here is just simple linear regression. So you see, this is my model here, and these are my inputs, you know, so this is my input space. Generally, it's going to be p-dimensional. So I've got p inputs describing the p dimensions, and this is just my linear model. So I have the p+1 coefficients all collected into this vector beta. Okay, so what these both of these regularizations do, they restrict the magnitude of the vector beta, right? They restrict the magnitude of those coefficients. You know, by doing this, you're sort of avoiding the situation of of a model that has, say, two coefficients with large magnitudes that cancel each other out. Because you can imagine a situation where you have terms, say beta 1 and beta 2, that are both large and cancel each other out, but that as you can imagine makes the model quite unstable. So the regularization of both types, as shown on this slide here, basically ensures that this doesn't happen by restricting the length of this vector beta. But if you look at the equations now, you will see that the way the length is restricted is different, right? So you can imagine that if you just look at the magnitude of beta, especially near near zero, right? So near zero, this function is just going to be like this, where this is a quadratic function, so it's going to go like this, smoother, right? So what that means is that the case of the lasso regression, in the case of lasso regression, in the first case, things are going to be more sensitive to the beta coefficients near zero, I guess. And this can be actually exploited for things like feature engineering, and as was done, for example, in this paper. So what they did in this paper, this is actually from Dick Zehr. Many of you will probably know Zehr, from his book on angular momentum, right? It's the same Dick Zehr. Okay, in any case, so what they did in this paper, they looked at the problem of optimizing chemical reactions, so what they had in their experiment, they had 3 parameters in the experiment that they could optimize. One was gas pressure, one was voltage, and one was flow rate. Okay, and in principle, one could work with this 3-dimensional feature space, and one could try and optimize these parameters and determine optimal combinations of those parameters. However, what if these features are not the best for the problem at hand? What if some combinations of these features are better for modeling reaction yields? So maximizing the reaction yield was one of the goals of this paper. Okay, so and this is a question that people will often ask in machine learning, because you don't actually know a lot of times a priori how to choose your features or variables that define your input space in the best possible way. Okay, so one way to answer this question, the question of which combination of these 3 parameters it can be better as features of the input space, could be like this. So this is what they did in this paper. So basically, they engineered new features as sort of combinations of P, U, and V. These sort of combinations, and there's 11 of them, I believe, that they put together this way. Okay, now using these new features as variables, they would train the 11-dimensional linear regression. Okay, and they look at the three main variables, in this linear regression that determine the variation of the output. Okay, now how do they do that? So for that they use lasso regression with this coefficient lambda that they would vary. So they would, so you can imagine that if you make this coefficient very large, this will suppress all of the coefficients to very small values, and only the one that contributes the most to the variation of the output is going to be present in the regression. So then you repeat the regression training. You retrain the regression, but with a different value of the lambda coefficient. And as you decrease it, another value of beta corresponding to one of this will pop up, and then another one, and this is how you can determine the most dominant of the features that contribute, I guess, to the variability of the output, which is the reaction yield in this case. And you see, lasso regression is more suitable for this particular problem than ridge regression, because, like I said, things are more sensitive more sensitive to beta coefficients at small values of those coefficients in the case of lasso regularization. Okay, so that's just an example that I wanted to show you from the literature. But which is basically to say that. So what I'm trying to say here is that there could be many reasons to use other types of regularization than ridge, of which this is one example. So, and there's many different ways to do regularization out there. So I don't know if, Anna, you find this satisfactory?
Yeah, definitely. So like we try to exploit this sensitivity around the zero, and there are, I guess, many ways of exploiting that.
Yeah, exactly. So that's, like I said, that could be one reason and one example, but there are many others. Okay. All right. So I think we're gonna move on now. So there's two basic but important concepts that we need to understand for today's discussion. So I've sort of mentioned this already. I mentioned this already yesterday, but I think we need to go through this carefully to make sure that we're all on the same page. So I'm going to start by the discussion of the Bayes theorem, because it is, of course, at the core of Bayesian machine learning, and this is something that we're going to be talking about today. And I also wanted to spend some time to talk about model likelihood, because this is one of those concepts that people a lot of times misunderstand. And again, we're going to be talking about likelihood and marginal likelihood, and so it's important for us to understand what likelihood is. Okay, so yeah, we're going to start with the Bayes theorem. The Bayes theorem is the basis of Bayesian inference, and it basically shows how a degree of belief must be modified to account for evidence or for observations. Okay, so Bayes theorem operates with probabilities or probability density. So and therefore the degree of belief must be expressed as a probability. Okay, so let's first define the notation here. So we're going to be talking about P of x as a probability if x is a discrete variable, for example, heads or tails for a coin toss. And then we're going to be dealing with conditional probabilities written like so. So this is going to be the probability of x given y. So if x is continuous, we must work with a probability density. Okay, and then the probability is going to be given by the integral of it. So that's going to be the probability that x is in the interval between a and b. Okay, like I said, in this case, this quantity here is the probability density. We'll also encounter conditional probability density, and we will write it either in this form or in this form. Okay, so by writing this, I'm going to say that the variable y has the value lowercase y here. Okay, that's just a notation. So the Bayes theorem, it's actually very interesting and very simple. So it is basically given by this equation here, and it says that for two events A and B, you have this relationship between the probabilities. So the probability of B given A is equal to the probability of A given B times the probability of B divided by P of A. Okay, and again, an event here is a realization of a random discrete variable. Okay, so I've got this problem here that should illustrate to you how how to apply the Bayes theorem. I've actually taken it from an article in New York Times that was describing some book, and they consider this specific problem. Assume that you're presented with 3 coins, 2 of them are fair, and the other one is a counterfeit that always lands heads. Now you randomly pick one of these 3 coins. The probability that is the counterfeit, of course, is 1 out of 3, right? Okay. Now this is your prior probability. So yeah, I guess we're going to be operating with prior and posterior probabilities. The prior probability is going to be this quantity here. That's the probability that doesn't account for any observations. Okay, that's the probability that we know that if we pick one of those coins up, it's going to be 1/3, right? So that's going to be our prior. This probability on the left-hand side, so the probability, conditioned by A, that's going to be our posterior. Okay. So now after picking the coin, you flip it 3 times, and you observe that it lands heads each time. Okay. So seeing this observation, and seeing that the coin that you've chosen lands heads 3 times in a row, okay, your goal is to calculate the probability, and that's going to be a posterior probability. It's going to be a posterior probability that the coin is counterfeit. So I'm not going to go through this calculation now, so I'm going to leave this for you to work out maybe in a coffee break. It's a nice little problem that will be an exercise in the application of the Bayes theorem. Okay, so I'm gonna maybe I'll put it back up during the coffee break, and perhaps you guys could chat and try and calculate this probability. I'm going to illustrate the application of the Bayes theorem by another example. Okay, and let's say you have an undergraduate student who wants to calculate the probability that he or she will get into a chemistry graduate program if she or he gets an A in first-year undergraduate chemistry, Chem 121. I chose Chem 121 because it's a course that I taught for many years. Okay, so rephrasing this in the language of Bayesian inference, this problem should read something like this. You meet a first-year undergraduate chemistry student, and the student asks you, what is the probability that I will be admitted into your graduate school? And then you say, well, it's 5/100. And the student will say, but I just passed Chem 121 and got an A grade. And then you say, well, in this case, the probability is 16.7/100. So how did you come up with this answer? So you use the Bayes theorem to calculate this. Let's see how you did this. Okay, so we're going to define the variables x and y, and x is going to be 1 if the grade in Chem 121 in the first year undergraduate class is A, and it's going to be 0 otherwise. And for y, y is going to be defined 1 if the student is in the grad school, and 0 otherwise. Okay, so we can calculate the probability of y equals 1 as simply the number of graduate students divided by the total number of undergraduate students, right? So that's your prior probability that a graduate student is going to, like any student that you choose is going to go to grad school, right? So now you could also calculate this conditional probability as the number of, so basically this is the number of graduate students with A in Chem 121 divided by the total number of graduate students. Okay, so that's going to be the probability, the conditional probability in the numerator of the Bayes theorem. Okay, and now the P of x equals 1, which is basically the probability of getting the grade in the undergraduate class is simply the number of A grades divided by the total number of undergraduate students. So your purpose is to calculate. Your purpose is to calculate what? Is to calculate P of y equals 1, given that x equals 1, right? So that's the conditional. That's the posterior probability that having gotten the excellent grade in Chem 121, you're going to get into graduate school. And this is not a trivial probability to calculate. It would not be a trivial probability to calculate had it not been for the Bayes theorem. But the Bayes theorem makes this trivial because it allows you to write this probability in terms of these 3 probabilities, right? For example, let's say you have 1 in 20 undergraduate students go to grad school. That gives this factor to be 1/20, right? That's your prior probability. So if you don't know anything about the student, you choose any arbitrary student, you're going to say that the probability of the student going to grad school is going to be 1 in 20. Okay, and now if you look at the number of graduate students and you ask how many of them got an A in Chem 121, that's going to be like, let's say 2/3. Okay, when they took it back a long time ago. Okay, so that's going to be your probability 2/3. Okay, Now, the number of A grades in Chem 121 in our university is typically 1 and 5. So this probability here is 1 and 5. So then you do this. So then this math becomes very straightforward, and that's how you calculate this probability, which is again the posterior probability. So this one is the prior. This one is the posterior. Okay. Any questions about this? So try to, yeah, go ahead.
Hi, in this example, you assume that having an A is one of the most important factors for becoming a grad student, right? So how often do you encounter problems like this in actual machine learning? Like you have to choose which variable will explain the most your station.
Yeah, thanks a lot for this question. I mean, I'm not assuming anything about, I mean, like the causality or relationship between the A grade and the admissibility to graduate school. I'm just saying that I just want to calculate the specific probability. There could be other factors that, of course, determine whether a person goes to grad school or not, and I don't know what those factors are. But I have what I have to work with, and I can use that to calculate the probability. Again, this is just a probability, and that's why it's going to be a lot less than 1 still, right? Because there's all these other factors that will determine the outcome. But yeah, I just have all these numbers to work with, and I use them to calculate that specific probability. It's all. Yeah, I guess what I'm saying is that it's all based on observation. So I'm saying that, you know, I'm observing, you know, I guess that a person has gotten an A in that course, and you know, so that observation, I guess the bottom line of this is that observation itself is going to modify the probability. Yeah, so I guess the main point of this example is this. So if I don't know anything about the person, the best I can do, if I want to predict the probability of this person going to grad school, the best I can do is 1/20, right? Because I know that 1 in 20 people go to grad school, okay? Now, if I know something about this person, I can modify this probability. I can make my prediction better, okay? So, and like if the person gives me this information that they got the A in this class, I can use it to modify my calculation of the probability using the Bayes theorem. That's the bottom line. I mean, that's I guess the main purpose of this example. So this example shows how you use observations to modify your predictions. This is, I guess, maybe let me skip down to what we're going to talk about later on. So it's let's look at this example here. So if we don't have any data points, we don't have any red points here, right? So what can we say about whatever quantity it is that we're modeling? Well, nothing, right? So we can try to model it with a distribution of functions that's going to basically, well, it's going to have some variance and it's going to have some mean, but you know, and we can choose the variance and the mean of that distribution based on certain beliefs, but that's the best we can do, right? So now once we have the observations, once we have these red dots here, what those red dots are going to do, they're going to condition our probability. So they will allow us to come up with a much better distribution, the one that's depicted in the lower graph here. And that's the one that we're going to use to make predictions. And so to go from the top graph to the bottom graph, we use the Bayes theorem. So this is basically an example of how observations, allow you to improve your predictions. Does this make sense?
Yeah, I guess in this case, you have a limited number of observations. I was just thinking, like, if you have too many observations, which one do you choose that would be the best? But in this case, it's... Well,
the more observations, the better, right? So it would be,
I mean, in the grad student case, let's say I mean, when this person tells you I have an A, you also have lots of other information, like they have glasses, whatever.
Yeah. So I get. Yeah. Sorry. Go ahead.
No. It's just that in general, maybe you have too much information, and so your update depends on which one you choose. No.
Yeah. So then of course the calculation. So what you're saying is that there may be some dependence. I mean interdependence of different factors, right? So and then you might have to worry about that. But if you have other factors that are independent that are given to you, you could use those to further improve the calculation of this probability, right? You could then you could complicate this calculation further and further to make the calculation of the probability better and better. So in that sense, the more observations you have, the better. So observations will never make your calculations worse. They will not always help. For example, if you have like perfectly correlated, factors, right, or features, adding those features is not going to help necessarily, but it's not going to make your predictions worse.
Yeah. Thanks.
Yeah. Okay. Makes sense. But the bottom line of this is that the Bayes theorem, and of course the essence of Bayesian inference is about using observations to improve your predictions. You can think of this almost like as an iterative approach, right? An example I saw on YouTube was about a person who has spent his entire life in a cave, and then he comes out one day and he sees a sunset and then or a sunrise, and then and then he wonders if this is a one-off event or he doesn't have any information to know anything about it, right? And then the next day he sees the sunrise again, and that allows him to modify his conclusion that this was a one-off event to perhaps to conclude that this perhaps is something that happens regularly. He wouldn't necessarily know how regularly yet, but then having seen this event multiple times, his conclusions would become better and better. And this theorem is actually quite beautiful because there's actually evidence that the way our brain works is very much determined by the Bayes theorem. We have a prior that is determined by our beliefs, and those priors are constantly modified by what we see around us. And one can do experiments to prove this, and we don't have time to talk about that, but there's actually some interesting videos on YouTube that illustrate. They would play a tape of some text that's scrambled, and the first time you hear it, you wouldn't understand what the text says, what the recording says, and then the person would play the clean version of it, so you would know what it is, and then he would play the original recording again, and your brain would now clearly recognize what the original recording is, because it would modify the prior by I guess what you would hear when a clean recording is played for you. So it's quite amazing, so you might want to look this up. Okay. So shall we move on to talk about likelihood? Right. So again, I wanted to talk about likelihood because it's again something that a lot of people misunderstand. They think of likelihood as a probability, which it is really not. So let's start by saying what likelihood is not. Likelihood is not a probability or a probability density. Okay. So it is equal to the probability or probability density, but it's not a probability. And so what do I mean by that? Let's see. So let's consider first the case of a discrete random variable, So we have a stochastic process that produces one of the values of x. For example, we have a coin that we flip, and every time we observe heads or tails, and and whether we observe heads or tails is determined by how fair the coin is. Okay, so a stochastic process is usually a function of some parameters beta. So in our example, the flip of a coin is a stochastic process, and the random variable is h or t, and the parameter beta is the fairness of the coin that will determine the outcome of the flip. Okay, so let's define this parameter as simply a continuous variable equal to the probability of observing h. Okay, we can define the model parameter the way we want, and let's define it as a continuous variable that's equal to the probability of getting h. So if the coin is fully unfair, you will, so that would correspond to the value of beta either equal to 0, in which case you will always get tails, or the value of beta equal to 1, in which case you will always get heads. Okay, all right. So now, given beta that's defined, we can calculate the probability of observing, for example, double h in 2 coin flips, right? So for beta equals 0, we will never observe h. So the probability is going to be 0. For beta equals 1, we will always observe h. The probability is going to be 1. For a fair coin, we know it's going to be 1/4. Okay? So what likelihood is, it's a function of beta given an observation. So likelihood is defined as equal to the probability of a particular observation given beta. Okay, so I can calculate this like up here. I'm calculating this probability, but the important distinction is that the likelihood is can only be defined after you have observed something. Okay, so in this case, likelihood is going to be a function of beta given the observation that the 2 subsequent tosses of a coin give us heads. Okay, now why do we need likelihood? Okay, let me illustrate this by this example. Let's say you have a coin, but you don't know how fair it is. So you don't know the parameter of your model. Okay, so likelihood allows you to estimate beta. Likelihood allows you to estimate the parameters of the model, and this is exactly what we do in machine learning all the time. So let's see how. So first, we're going to note that likelihood depends on the observations. Again, I already said this, but this is very important to keep in mind. So if you flip the coin twice and get HH, so then we can calculate likelihood as a function of beta. We can calculate it, and it's going to be the red line here, right? So now for 3 coin tosses producing HHT, it's going to be the green line. For 4 tosses producing HHTH, it's going to be the blue line. Okay. Now what you're going to do, so the likelihood itself is actually not really important. What is important is the maximum value of the likelihood, because this is what's going to tell you what is the most likely value of the beta given the observations. So if you only toss your coin twice and you see this outcome, the best you can conclude is that your coin is fully unfair with beta equals 1. So this is going to be the maximum value of your likelihood, right? So now if you flip the coin the 3rd time and you see that tails, then you have to modify your prediction of beta. Again, you look at the value of beta that corresponds to the maximum of the green curve, and it's going to be somewhere up here. So you have to say that beta is equal to something like 0.7. Okay, you flip the coin again, you get HHTH, you get an H as an additional observation. So you have to modify your prediction of beta again. What you do, you look at the maximum of this curve. And so this is going to be your maximum likelihood estimation of beta, and it's going to be closer, of course, to the beta equals 1 level value. Okay, so this is how we use likelihood to estimate the model parameters. You can think of beta as the model parameters. Does this make sense?
There's a question.
Yeah.
Sorry if this may be a stupid question, but is there a real functional form for these curves, or is this just like a pictorial depiction of what's going on?
For this particular example, it's easy to calculate the functional form because I assume that beta is defined as equal to the probability of H. That's why I can calculate. So basically, so likelihood of beta given HH is just going to be equal to beta squared, right? And so in general, it will depend on the problem, right? Whether you're going to have a particular functional form or not. In this particular case, it's very straightforward to calculate these curves. Do you know what I'm saying?
So, but how would you get H for the curve for HHT?
Yeah, so that would be beta times 1 minus beta.
Okay. Yeah. Thanks.
Do you know what I mean? Yeah.
Yeah.
Okay. Good. Right.
Sorry. There is one more question.
Yeah. Go ahead.
Sorry.
Yeah, no problem. Is there another question?
The mic was not working now. So I have also a trivial question, because you started by saying that the likelihood is not a probability, but then you define it as a conditional probability. So is there something?
Yeah, so it's very important. The likelihood is equal to the probability. You see, it's equal to the probability, but it's not a probability. So you cannot say that this function is a probability of observing beta given HH. You cannot say that. So it's equal. It's a function of beta that is equal to the probability to observe HH for that particular value of beta. See what I mean? So if you don't have any observations, you cannot define likelihood. So you have to have specific observations in order to define the likelihood function. Do you know what I'm saying?
Yeah. Okay. Thanks.
Yeah. So when you look at these curves, therefore, you cannot say that the probability of beta, this value of beta, is going to be bigger than the probability of this value. So that is wrong to say it. So likelihood is not the probability. So the only thing that matters is the value of beta that corresponds to the maximum likelihood. So that's the thing. That's the only thing that matters. And you can actually So I'm saying this here. So again, in words, note that on the left-hand side, x is not a variable. It's a fixed outcome of a random variable. And we should not confuse this with the probability. It is wrong to say that this is the probability that beta has some value given an observation. So this mistake has been made, many times in courts, and actually it has led to some devastating consequences, which you can read about on Wikipedia. It's quite interesting. So that's why, it's really important to understand how to work with likelihood and not to confuse it with probabilities. Now, if our random variable is continuous, likelihood is defined as equal to the probability density, like so. So it's a straightforward extension of the discrete case. But again, that's just how you define the values of the likelihood. And that's how you can calculate the function of the likelihood function as a function of beta. And then what you can do with that function, you can determine you can maximize it to determine the value of beta, and that's going to be your maximum likelihood estimate of the model parameter beta. Okay, so you may notice that terms like this or terms like this, they will. It's one of the terms in the numerator of the Bayes theorem. So there's going to be a likelihood appearing in the Bayes theorem, when we apply it to machine learning models. Okay, can I move on now? Are we good?
Yes, I think so. Thanks a lot.
Good. Yeah. Okay. Let's go back to our discussion of Gaussian processes, because pretty much the rest of what we're going to be doing today and tomorrow will involve Gaussian processes. I'm going to go through some of the most important results that I already mentioned yesterday. And again, I'm not going to show any of the math. You have those equations, I guess, in the notes that I sent to Anna yesterday. there may even be some mistakes in those equations because I put them together very quickly. So if you find anything that's a problem, or if you have any questions, please by all means feel free to get in touch so we can discuss this. In any case, so we've already learned a general regression tool, which is kernel ridge regression, which is a very good machine learning tool. It's used for many applications. So the question is, why do we need another regression model? So Gaussian process regression, as we saw, the prediction formula that we use to make predictions with Gaussian process models is exactly the same as in kernel ridge regression. So Gaussian process regression, it will do the same as what a KRR can do, but it also allows us to calculate the Bayesian uncertainty of our predictions. Okay, it's the uncertainty basically due to the finite number of observations, okay, or the lack of certainty because our observations are necessarily finite. Okay, and as we can see, this can be used for two important applications. One is Bayesian optimization, and another one is building better kernel functions. Okay, so how did we get Gaussian process distributions yesterday? So we started by saying that, okay, let's consider a model, like a linear model in some high dimensional space, which is determined by those functions here, phi and phi of x, and so this sort of a model can be depicted. It's a special case of a neural network, I guess. Can be depicted as a neural network. Okay, so if all of the parameters of the neural network are fixed, then of course the neural network is going to be deterministic, and it's going to produce for each value of x a single value of f of x. So what we said yesterday, that we're going to make the weights of the inputs into that neuron here, the beta coefficients, we're going to make them random variables. Okay, each is going to be distributed according to some distribution, and since the variables are random, each time we draw a value for each one of these betas and evaluate the neural network, it will produce a different and random result. So the output of the neural network for fixed x is going to be a random variable, and we can plot the outputs as a function of x. And then we're going to have something like this, where each curve is going to correspond to a different combination of beta naught through beta n. So you can think of each curve as a model of your data. So we have now many, many different models. Okay, so they're all going to be models with the same functions phi. They're going to be linear in that space, but they're going to correspond to different values of the beta coefficients. Okay, so again, to model the data, what we want is to somehow change this distribution. We want to condition this distribution of functions by our observations. So we want to go from this to this. Okay. And so basically, yeah, in the language of equations that we introduced yesterday, we want to condition our distribution, which is P of theta. So X here is a matrix of vectors that specify the positions of the data points. So if our input space is P-dimensional, so this is going to be a matrix of P-dimensional vectors. There's going to be P columns or P rows in that matrix, and there's going to be as many columns as the number of data points. Okay, so we're going to be looking at, and theta is going to be describing the beta coefficients collectively, because I don't want to write beta naught through beta n all the time. Okay, so what we want is to go from this sort of distribution to one that's conditioned by the observations y at the positions of the training points. Okay, so the Bayes theorem gives us this conditional distribution. So we can write it like this, and now we can recognize that this is going to be the model likelihood. Okay, so you see, this is going to be our prior distribution. So it's the prior distribution of theta, so which we actually are free to choose in whatever way we want. So the better we choose the prior, the more efficient the predictions will be, meaning that the fewer observations we will need. And it sort of makes sense, right? If we know the model, if our model is already what it should be, and let's say we know it up to some scaling factor, then we only need one observation to fix that scaling factor, and then we're done with our predictions. Okay, so but generally we don't know the model a priori, right? So that's why our prior will require some choice based on our beliefs, and even if there is no belief, we can choose it like pretty much arbitrarily. But with Bayesian modeling, the better you choose the prior in general, the better are going to be the predictions. So this is a statement that we may want to remember, because we're going to come back to it when we talk about building better kernels for Gaussian processes. Okay, so this is the prior. So this is going to be the model likelihood, or it's the probability, and as you can see, it's going to be equal to the model likelihood, as we discussed earlier today. Now this term here is going to be important. As you can see, this term here is just the integral of the numerator over theta. So, and I don't have it written here, but you can imagine that if I take the numerator here and integrate over theta, I'm going to get this term here. Okay, this term is the probability of observing your data, and it's called marginal likelihood. It's called marginal likelihood because it's equal to the integral over likelihood times the probability times the prior, which basically is sort of like the weighting factor of different realizations of theta. Okay, so now once we have this in Bayesian machine learning, we make a prediction. We make a probabilistic prediction, and the probabilistic prediction is made using this integral. So this basically is the probability density of theta given basically your observations at the positions of the training data. Okay, so what we want, of course, is to make a prediction of this whatever this observable is at x star. And we do that by taking this, and then this is this red part here, and we're going to multiply it by the probability to observe y star at x star given a particular model, like corresponding to a particular value of theta, and then we're going to integrate it with theta. Okay, so in this way, actually, the prediction comes in the form of average over multiple models. Okay, not just one model, but multiple, I guess, models, and that makes this powerful. So there's a question in chat. Unfortunately, I can't read the chat, I guess, in my current mode, but if somebody could read it for me.
Yeah, sure. Hold on.
It must be a private message because we can see it.
Oh, you can see it. Yeah. Oh, okay. Sorry. The question was about X and Y. So let me repeat what X and Y is. X is a square matrix that specifies the positions of the training points. Okay. Let's say you have a three-dimensional space. So every point in this three-dimensional space, the position of each one of those red dots, where are they? Yeah, the position of each one of those red dots is going to be specified by a three-dimensional vector. And let's say you have 5 dots. If you have 5 dots, you're going to have a collection of 5 three-dimensional vectors. That's your X matrix. So it's called the data matrix. So it's a matrix that encodes the positions of the training points. And Y here is simply a column vector of observations that correspond to those specific positions of the training points. The Y's are the actual values of the observations. Does that answer your question? Yeah.
I have another. I have another question.
Yeah, go ahead.
Maybe you've said it, but I'm a bit confused because at the beginning you said that Gaussian process regression does essentially what kernel ridge regression does, but with this Bayesian uncertainty. But I don't see. To me, it looks like a completely different method. So where's the analogy to kernel ridge regression?
Yeah, it is, quite different, but it works out to be the same, as we will see maybe in a couple of minutes. So if you look at the formulas for the prediction, they actually are identical. So yeah, so I'm not going to go through the math. It's in the notes I sent you yesterday, but I am going to show you the final results. Just give me, I'll come back to your question in just maybe 5 minutes. Let me continue for now, and I'll come back to this question.
Okay.
So yeah, so I guess what we were saying yesterday is that if we take this neural network and then make the let the number of neurons in the hidden layer go to infinity, make them that number very large, then of course what we're going to have, each one of them is going to produce as output a random variable, and we're going to have a sum of a large number of random variables. And if they are all independent random variables, and this number is large, then the sum of them is going to give us a Gaussian distribution, and that by the central limit theorem. Okay, and of course the distribution is going to remain Gaussian for every value of x. Okay, so this is what I'm depicting by this graph here. So if you take this ensemble of random functions, and if you look at the cut of this ensemble in this direction, then you're going to have a Gaussian. Okay, so now this helps a lot because the integrals, like these integrals here, for example, in the case of Gaussian processes, they can be done analytically, because otherwise we would have a problem, because the number of these data parameters is very large. So it's very difficult to do this kind of integrals. Not impossible. You know, there are methods to deal with this approximately using, for example, Markov chain Monte Carlo, or you know, other approximations. But you know, you can't really. Yeah. So, but it's difficult, as you can imagine. So, but Gaussian processes allow one to calculate these sort of integrals analytically. So we can have we can calculate this probability. So you see, this is the what we would call the predictive probability, because it gives us the probability to observe y star at x star. So it's going to give us a distribution of values at x star, and we can use the mean of that distribution, for example, as our prediction. That's what we're going to do. Okay, so right, so the math that then follows can be done analytically, and this is what's done in the notes I sent you yesterday. So you can take a look at this if you wish. But the final equations are this. So this is the equation for the mean function. So this is this green function that basically is the mean function of that distribution of functions, and this is the equation for the standard deviation. So if you look at the Gaussian at a particular value of x star, like at this value of x star, there's going to be a Gaussian distribution, and the mean of that Gaussian distribution is going to be given by this formula, and the variance is going to be given by this formula. So this is the conditional mean and the conditional variance, and this is, both of them are written in terms of the kernel metrics and the vector of kernel functions, which are exactly the same as the ones we saw in kernel ridge regression. So let's look at, I'm sorry for going for so long, but we're going to look at this and then take a break. So let's look at this equation in particular and compare it with what we saw for kernel ridge regression. So for kernel ridge regression, the equation for the model prediction is this, which is identical to what we have in the Gaussian process regression case. I mean, the difference is in this term here. So in the kernel ridge regression, this term is basically it's the regularization prefactor, that parameter lambda times the identity matrix. And here we have sigma squared, which is the unconditional variance of the Gaussian process. Basically, this is the variance of the noise. Okay, so which we can also fit. This could be a parameter, that we could treat this as a parameter, as a variable parameter to fit the noise if we don't know the variance of the noise. But a lot of times we're going to keep this fixed, just like this parameter is kept fixed in kernel ridge regression. So this is what I mean when I say that the prediction of Gaussian process regression is, boils down to the same, I guess, result as the prediction of the kernel ridge regression. Okay, but we don't have this. We don't have the middle equation in the case of kernel ridge regression. Okay. So now there's another, okay, I don't have it written here, but there's another important difference between kernel ridge regression and Gaussian process regression. And this is in the way the models are trained. So, and by that, I mean in the way the parameters of the kernel function are determined. Because like this kernel matrix here and this vector here, as you can remember, is parameterized by kernel functions, which we have to choose somehow. And there's going to be parameters and there's mathematical functions that define it, that give us the kernels. And those parameters have to be chosen somehow. Now, again, the way you would choose those parameters in the case of kernel ridge regression, you would calculate this, and then you would you have a holdout validation set. Okay, like you split your data into a test set and a validation set, for example, and then you use that validation set to calculate the error given the model, and then you vary the parameters of the kernels, for example, using grid search to minimize the validation error. Okay, normally we would do that by cross validation. Okay, and in the case of Gaussian processes, you don't do that. In the case of Gaussian processes, you actually maximize, and we're going to talk about this a little later today, you actually maximize marginal likelihood. So you have likelihood for the model, then you integrate that likelihood over the beta parameters or theta parameters in the language of what we just saw. And then that gives you marginal likelihood. And that marginal likelihood can be written in closed form in terms of the kernel matrix and kernel functions. And then you vary the kernel function parameters in order to maximize marginal likelihood. So the way you arrive at the kernel functions is different. And but the final formulas for the predictions are actually identical. Does that answer your question? I don't know who it was.
Yeah, I will pass the microphone.
Yeah. So I think we should take a break now. But I mean, let me let's see if this question is answered.
Okay. I guess it does answer the question. I think the confusion came from you skipping the equations and me not being sure where the kernel came from and like how it all came to be. But I mean,
yeah,
I see the similarity in the equations.
Right. So yeah, it's the math is in that in the notes I sent you yesterday. I understand it's a little bit overwhelming, yeah. So I don't. You could try to look at that and let me know if you have any questions about that. And there's many different ways to actually look at this, and I just followed the approach in one of the books I like, but. Yeah, so I guess I don't think we want to spend too much time looking at that math. I think more productive ways of using our time.
Yeah, no, it's fine. But it also, the Gaussian process regression also uses a kernel trick of some sort at some point in the derivation.
Yes, so maybe we could, how about, can I use the break time maybe to go through some of those equations? I don't know. So maybe whoever wants to take a break should take a break, and I could maybe, do you want me to go through some of those equations to show you how this equation arises? Or you have it in the notes I sent you yesterday, but yeah, it does arise. Like it probably will take us more than.
Sorry to just, I mean, I think we should take a break, but then, I mean, I think we can come back to equations after the break if it's okay for you, but I mean.
Yeah, so maybe we can meet like 10 past 10, then we have, right? So in
Sounds good.
bit more than 10 minutes. Yes,
So,
thank you. And just technical reminder for people here, like that our proper coffee breaks are at 11 a.m. and then at 5 p.m. So of course, if coffee is there, you can use. Usually now it's still warming up, but please have in mind that somehow to planning your coffee consumption to do it on the main coffee breaks, and now use just for relax and discussing the lecture. Okay, thanks.
I'm gonna put this up on the slide so you could maybe talk about this during the break if you want to maybe solve this little problem here.
thanks.
Yeah. All right. See you in 10 minutes.
Hello, we are back. So we can start second part. If one is here. So please take seats.
Just give a second. Oh. Let's screen. Okay, I'm ready. Shall I go ahead?
Yes, please.
Okay, good. So that's where we were. I suggest that we continue with the discussion of application space now to physics problems, because I was going to talk about Bayesian optimization next, which is a very interesting and useful technique that I want you to learn about. And then we can come back maybe to the discussion of the math. I don't know when, we can have time for that. Like I said, the derivation of these two equations is in the notes. I mean, like it's a bit messy, but it's in the notes that I sent to Anna yesterday. So you could take a look at this and let me know if anything is not clear. Okay. But what I wanted to focus on now is this term, this term, the one in the middle. Again, this is the conditional variance that comes out as one of the, was a byproduct of Gaussian process regression. And this is basically a measure of the Bayesian uncertainty of the Gaussian process model that you build. And what this can be used for is as a very efficient optimization technique that's called Bayesian optimization. Okay, and this optimization technique, it's a machine learning optimization technique, is very useful for applications where you have to optimize expensive black box functions. And by black box functions, I mean functions that we don't know. And so it's particularly useful for functions that are very expensive to evaluate, because as we will see in just a moment, this is a gradient-free optimization technique. And I'm going to illustrate the efficiency of it by some of the examples from our research work. Okay, so it can be used for example, for many interesting applications, of course, in physics and chemistry. And one example of applications it can be used for is the self-driving labs, where you have some experimental parameters that determine your experiment, and you want to achieve a target of some sort. So you could determine the experimental parameters by these sort of feedback loops. Okay, and this can be done very efficiently with Bayesian optimization. And as we will see in just a moment, Bayesian optimization relies on surrogate machine learning models, A of X, that basically simulate the experiments. And those surrogate models in our example are going to be Gaussian processes. Okay, so we're going to talk about inverse problems, or applications of these to inverse problems. And in the context of inverse problems, we need to think about it like this. So let's say you have some theory, like for example, quantum theory, that is parameterized by unknown parameters, by say the Hamiltonian parameters that we don't know. In the context, for example, of molecular dynamics, let's say you have the interaction potentials that determine the interactions between molecules, but let's say you don't know them well enough, and you want to determine those potentials. You want to make sure that those potentials, they correspond to some experimental observables. And again, you can formulate this as an optimization problem, where you perform a theoretical calculation, compare it with the experimental measurements, and then you minimize the difference between the theory and the experiment by varying the parameters that determine your theory. So I suggest that you read this paper if you have time. This wonderful paper I wrote a couple of years ago that discusses all sorts of applications of this kind. In chemical molecular, in quantum molecular dynamics. All right, so how does Bayesian optimization work? So like I said, Bayesian optimization is designed to optimize unknown functions without gradients. So, and for that reason, it's particularly well suited for functions that are very difficult to evaluate. Is there a question?
Yes, sorry, I have a question.
Yep.
Could you comment a little bit on in what kind of situations would one use Bayesian optimization as compared to just normal regression models or like neural networks or stuff like that? So when would you decide to, when would that be the best method to use?
Yes, it's a very important question and an easy answer for this one. So you would want to use this method, Bayesian optimization, when the function you're optimizing is extremely expensive. For example, if you're optimizing your experiments, and let's say each experiment takes a month of work, so you can't afford hundreds of experiments, right? You want to be able, and let's say your parameters, parameter space is something like 10 parameters. You have 10 parameters that parameterize your experiment, and each experiment takes a month of work. So so you can't afford thousands of experimental results to obtain. So this is what this is going to be particularly suitable for. So you want to be able to optimize with very few experiments. Okay, so that's, and because the function is so expensive to evaluate, so in this particular case, the objective function is going to be your experiment, right? The outcome of your experiment. And because it's so expensive, you can't really afford to calculate gradients. Like anything that uses neural networks is going to require gradients, I think. This method is gradient free. Okay, is this clear enough?
Mm-hmm. So like a small number of measurements would be like order of 10, orders of hundreds, or
so I'll show you examples. I'll show you examples from our work, but a rule of thumb is that you should be able to converge this sort of optimizations with 10 times the number of parameters that you're optimizing. Like if you have 10 parameters, you should be able to converge the sort of optimizations with 100 of experiments. So that's a rule of thumb that, and you can actually make this more efficient by, for example, designing better kernels of the surrogate models. And this is going to be one of the points of my presentation today. And you could do other tricks. There's going to be two parts to Bayesian optimization: the kernel of the surrogate models and the acquisition function that could be modified to make it more efficient if that's necessary. But the rule of thumb would be about 10 times the number of observations. The number of observations should be 10 times the number of parameters. Okay. All right. So how does this work? Okay. So we're going to use Gaussian processes as surrogate models of the black box function. Basically, we're going to do, if you go back to this loop here, we're going to produce well, let's say we're going to solve an inverse problem. So let's say we want to develop a theory that produces a perfect description of an experimental observable. So the objective function will then be the difference between the theory and the observable. And so we're going to start with selecting the parameters of our theory, say at random, and that's going to produce some theoretical result. And the difference between the theory and experiment is going to be some number. We're going to do a bunch of those, let's say 10 of those sort of calculations, and that will produce 10 values of the objective function. And we're going to use those 10 values to train a Gaussian process. Okay. And from there on, the goal is going to be to improve that Gaussian process. So each time we run a loop, we're going to have another theoretical result, and that theoretical result is going to be added to the training points of the Gaussian process, which by the Bayesian approach is going to improve the quality and the predictive power of the Gaussian process. And that Gaussian process is going to drive the optimization, as I will explain in a minute. Okay, so how does it work? We're going to use Gaussian processes as surrogate models. Okay, again, this is going to be an essential part. So the Gaussian process, once you train it, you're going to have the mu, and you're going to have sigma squared. Okay, so then you're going to build an acquisition function, and there's several ways to build what we call an acquisition function. So this acquisition function is going to tell us where to evaluate the objective function next. Okay, and this is the simplest way to build an acquisition function, which is simply a balance between the mean of the Gaussian process and its uncertainty. Okay, with some coefficient here, kappa, that you would choose, like, you would fix it to something like 0.001 or something like that. Okay, so again, I know what you're gonna start with is a bunch of points in the X space. X is your input space. You're going to train a Gaussian process. This Gaussian process will produce mu hat and sigma hat squared. You're going to calculate with that Gaussian process this function alpha x. So this function is easy to optimize. You're going to optimize this with some whatever optimization technique is of your preference. You're going to find the value of x that corresponds to the maximum of this function, and this is where you're going to evaluate your objective function next. So this is, for this value of x is if x is the bunch of experimental parameters, so this is the next batch of experimental parameters that you're going to perform the experiment for, and then you're going to iterate this process. Okay, and by doing this, like I said, every iteration is going to make mu and sigma is going to make this a better description of your objective function, and it's going to reduce this part. So if you look at the limit of the maximum of the infinite number of observations, this part is going to reduce to 0, right? Because if you know everything about your function, then the uncertainty is going to be 0. And then the maximum of the acquisition function is simply going to correspond to the maximum of the Gaussian process, of the mean of the Gaussian process, which will be a perfect description of your objective function. Okay, so this is how it works. I guess this is a pictorial depiction of it. Let's say you have some function which looks like the green function here, and so your goal is to find the global maximum of this function, like this one here, for example. And so you're going to start by evaluating this function at a bunch of points, and this is my iteration number 1. So I'm going to evaluate it at these 2 points, for example. And then I'm going to use these 2 points to train a Gaussian process. And what this will produce is a Gaussian process that's depicted by this ensemble of gray curves here. Okay. Then the question is, where do I evaluate this green function next? Okay. And so the acquisition function that's going to tell us where to evaluate it next is going to balance the mean of the Gaussian process with its uncertainty, right? It will look at what it knows about this Gaussian process and say, well, the mean of it goes up here, so perhaps the next evaluation should be up here. Okay. Now, a traditional gradient-based optimization technique would get you stuck here. But the Bayesian optimization will then say, okay, well, we know much about we know a lot about the objective function in this area of the parameter space, but there's a lot of uncertainty about it out here. So perhaps the next evaluation of the function has to be out here, and that's exactly what happens, and that's what takes you away from this local minimum trap. Okay, and that's, so the next evaluation, I guess, is going to be somewhere up here, because again, the algorithm is going to recognize that the gradient of the mean is going to go up in this direction. I'm going to pause here to see if there's any questions about this.
So it's correct to. Sorry.
Go ahead. No, go ahead.
Yeah, just to make sure that I'm following everything correctly. So you make the next evaluation where basically the uncertainty is the greatest.
Well, not necessarily. It's going to be a balance between the uncertainty and work. So you want to always go in the direction, of the gradient of the mean of the Gaussian process. because that's going to be the direction towards the maximum of the function. But you're going to balance that desire to go in the direction of the gradient by the uncertainty of the Gaussian process. Like if you go back and look at this function, you see, so you're gonna evaluate your function where this function, which is the balance between the mean and the uncertainty, is the largest. So yeah, so if you have a lot of uncertainty in your Gaussian process, your evaluation of the objective function is going to be driven by the uncertainty. But having done a lot of evaluations of the objective function, your uncertainty is going to be reduced, and the evaluation of the objective function is going to be driven by the magnitude of the mean of the Gaussian process. Does that make sense? So the beauty of this is that this is all, so this is changing dynamically. You see, like this sigma squared gets smaller and smaller as you get more and more, as you add more and more points.
So the mean of the Gaussian process will then, in the end, be equal to the value that you take for your function, right? I mean, that's your estimate of the function.
That's right.
Right. And so is this acquisition function, so that can be derived analytically as the most optimal acquisition function, or one could take other choices of the acquisition function and maybe?
Yeah, that's right. There are many choices of the acquisition function. So this is one that's used very, most commonly. But you could balance. So the key is to balance mu and sigma squared. So basically, this is what people call the exploration-exploitation balance. So when the evaluation is driven by this term, you're exploring the parameter space. When the evaluation is driven by this term, you're zooming in on the local whatever maximum you're in the nearest to. And so that's the exploitation-exploration balance. And yeah, there are many different acquisition functions that people use. This is just the simplest one.
Okay, thanks a lot.
Yeah, make sense?
Okay, yeah. I'm a different person, but I also have a question. So one is, you said that the next point is probably going to chosen to the left of the tree. This is because it already knows there's higher points to the left. Is that the reason?
No. So the Gaussian, at this point, the Gaussian process doesn't know that there is a maximum here.
Yes. No, I talked about you said the next point after the tree would be chosen to the left.
Oh, after the tree. Yeah, that's right. Because you're going to have a Gaussian process that will do something like the mean is going to go like this, right? And it will know that the function value is likely to be above this and this out here. That's why I think the next, if I look at this Gaussian process, I think the next evaluation is going to be somewhere out here.
Okay, and then one more question is, what if the green function has some uncertainty itself? Like from experiment, you can't determine it to like perfect accuracy.
No problem. It's a very good question, and this is exactly what this technique is ideally designed for, because remember when we train a Gaussian process, we include this parameter here, and we could actually treat this parameter as a variable parameter. So this parameter here describes the noise in your data. So basically, so this green function or the mean of the Gaussian process will then basically fit the background. I mean, like fit your true data, without the noise, right? So basically, it will remove the noise from your data automatically. So when you're training a Gaussian process, you're training, you're simultaneously also determining not just the model of the data, but also the model of the noise. I'm assuming it's Gaussian noise.
Okay.
Yeah.
Just
so
for this depiction, it just looks like at the point where you have the measurements, you basically take there to be zero uncertainty, which is a bit counterintuitive to me right now.
So right now, so each one of those observations, so I guess you're saying is that now we're gonna give some noise to each one of those observations, right?
Yes, basically, because we don't know
Yeah.
green exactly.
But that's not gonna matter, right? Because I don't have those pictures readily available, but remember yesterday, the graphs I showed yesterday, if you have this noisy data, and when you train a model, it's going to go through something like the mean of those noisy data. And so this Gaussian process is going to account for the for the noise in the data. So basically, then the objective function that the Gaussian process will infer if you have noise in the data is not going to go right through the data, but it's going to go through the mean of the data.
Okay, thank you.
Yeah, but yeah, so this is the beauty of it, because it can be readily applied. It actually works better for data that have noise than for data that don't have noise. Because if you don't have noise in the data, you actually have to include noise in your model, and then you have to take the limit of zero noise, and that may lead to some problems sometimes. Yeah. Okay. So yeah, I'm going to show examples from these couple of papers.
There's one more question, please.
Yeah, sure. Go ahead.
So given that we are going to get into kernel optimization, does this kind of thing happen for any kernel, or like the fact that you seem to be getting better at all the time when you pick a new point, does this happen for any kernel? Or?
Yeah, so what the type of the kernel will determine is the number of evaluations that you need to converge to this maximum. But with it, as you can imagine, with an infinite number of evaluations, you will always infer this maximum. So yeah, it will. This will work with any kernel. So what the different kernel what the choice of the kernel will determine is how fast you get to that point. And I'll show an example that illustrates this.
Okay, thank you.
Good. All right. Yeah. So this I believe in this work of ours, this was the first time we actually that someone actually looked at the effect of kernels on the efficiency of Bayesian optimization. Because normally people would just use something like the RBF kernel and they're going to be happy with this, because normally people can actually afford to do thousands and thousands of iterations, except that in applications in physics and chemistry, like I said, if we are trying to optimize time-consuming experiments or time-consuming calculations, we can't afford too many training points. And so we the focus of much of my group's work is actually on designing methods for something like Bayesian optimization that will converge with as few iterations as possible. Okay, so we're going to start by discussing the inverse problems, and again, I guess you all know about inverse problems. So in general, when it comes to, for example, scattering problems, like whether it's atoms or molecules or in general waves that are scattering. So we have the microscopic interactions that determine the interactions between microscopic particles, and those interactions, they parameterize typically quantum theory that will produce a set of equations that we solve to predict observables. And so and the purpose, of course, is to predict the observables of a scattering experiment. So what inverse problems do, they basically try to infer information about the microscopic interactions. For example, the interaction potentials between atoms and molecules that would correspond to the observables in a scattering experiment. Okay, and one way to do this is by these sort of feedback loops, where you start with the computation of a potential energy surface that describes the interaction between atoms or molecules, and then you parameterize you simulate your theory by a Gaussian process, and well, I guess you simulate the potential energy surface by a Gaussian process, and then you simulate a theory, the outcome of your theoretical calculation by another Gaussian process. So this is what we're going to do in my example today. So the first example I'm going to look at is the chemical reaction of the H atom with the H2 molecule. It's a three-dimensional system. And okay, so what this graph illustrates here is the convergence of Bayesian optimization. And again, let me explain to you again what we're doing here. So the black curve here is the dependence of the reaction probability on the translational energy for this particular reaction system. And like I said, typically the black curve would be calculated by solving the Schrödinger equation with a given potential energy surface for the H plus H2 system. It's a fairly complex calculation, so the potential energy surface is generally complex. Okay, so the black curve is the one that we took from the literature. So in this exercise, we wanted to see how quickly we can converge to the black curve, by massaging the potential energy surface of this three-atom system using Bayesian optimization. So we would start with a random guess of the potential energy surface, then solve the Schrödinger equation to produce the reaction probabilities as a function of the translational energy, and that would give us the blue curve, right? And then, of course, we would use the results of these calculations in the Bayesian optimization approach, as I described. And what this figure illustrates is that with as few as 8 iterations, our calculations would produce the red curve, which is almost on top of the black curve. Okay, so this is the potential energy surface that comes out of these calculations. It's a three-dimensional surface, like I said. And one point I want to make is that every time at each iteration, so basically what you're doing, you're changing the potential energy surface completely, right? So you're massaging the surface completely, and so Bayesian optimization somehow very efficiently is able to determine how to change the surface in order to bring the results of your calculations in alignment with the previous literature results. Okay, one of the things that we can also do with these sort of approaches is to answer the question of how many points, how many ab initio points you actually need to define this potential energy surface. So because typically the way people would calculate reaction probabilities, again, they would start by calculating this potential energy surface at a large number of points in this three-dimensional space, and then they would I guess this is and then they would produce some fit of that surface, and that fit would go into the Schrödinger equation. The Schrödinger equation would be for the nuclear dynamics would be solved to produce the reaction observables. Okay, now to produce a fit of this surface, and I did a lot of this kind of fitting when I was a graduate student. So this is actually a very time-consuming job, because imagine fitting something like this with a bunch of analytical functions. So it's not easy, and it requires a lot of points in this three-dimensional space. So this particular surface, I guess, the one that people use in the literature, was calculated, was obtained based on 8,700 points. Now, our approach starts with just a few points, like 10 points, randomly thrown into this three-dimensional space, and then we're adding one more point at a time, but we're placing that point not just randomly anymore after the first 10 points, but we're placing that one point in a position in this three-dimensional space that produces the most accurate Gaussian process model of the potential surface. And if you do that, you can get the red curve here, which is the result of the quantum scattering calculation, based on a GP model of a potential energy surface obtained with only 30 points. So as opposed to 8,700 points, you only need 30 points to represent the potential energy surface. So here's another example for a six-dimensional reaction system, OH plus H2. Same story here. Because the dimensionality of the system is bigger, we need more points, of course, to represent the reaction dynamics accurately, but it's still a very small number compared to what people typically would require to build the potential energy surface, if we wanted to represent it by some sort of analytical fits. So the black line here again is taken from previous work where the potential energy surface for this reactive system was obtained with 17,000 points. So 290 points that we need to calculate to basically obtain the green curve here, versus 17,000 points that gives the black curve here. So this just illustrates the efficiency of the approach that I described today. Any questions?
Yeah, I have a question. So you mentioned this yesterday. How does the efficiency of Bayesian optimization scale with the dimensionality?
Yeah, like I said, the rule of thumb is 10 times the number of dimensions. So for a 6-dimensional system, you would expect a fairly good representation with 60 or so, I guess, observations. In this case, we found that we needed close to 300 because it's a fairly low dimensional system. Actually, the higher the dimensionality, the closer you are to the 10 times the number of dimensions rule of thumb. But yeah, so if you have a 50-dimensional system, you should be able to describe, I guess, to converge a Bayesian optimization with something between 500 and 5,000, I guess, observations. It of course depends on the complexity of the objective function. If there's a lot of local minima, if it's highly non-convex, it's going to be harder to optimize it, but it's still going to be quite efficient. I would say between 10 times the number of dimensions and 100 times the number of dimensions. So for a 50-dimensional system, you would probably converge your optimization with between 500 and 5,000 observations.
So for chemical reactions, you'll always beat the naive approach, no?
What's that?
You'll always beat the naive approach for chemical reactions, it seems like, no?
So you mean like, so the number I'm saying is always going to be much smaller than this?
Yeah.
Yeah, definitely.
Yeah, okay.
Yeah, for sure. Yeah.
Thanks.
Yeah. So this is an example from the other paper. I mentioned the second paper that we published last year, where we actually looked at the possibility of reconstructing the reconstructing the molecule's polarizability tensor from, for example, from time-dependent quantum observables, such as the alignment signal. For example, let's say you have an alignment or orientation. This is actually the orientation.
I have a question.
Yeah.
So you're inferring the potential energy surface from the reaction probability, right?
Mm-hmm.
So couldn't it be that your potential energy surface has some errors which you cannot infer from the reaction probability itself? Like you're probing only the reaction channel, right?
That's right. So it could, but I don't care about these errors as long as my goal is to calculate the reaction probability, say the cumulative. So this is, of course, so we're getting into a discussion that gets me in trouble with chemists all the time, because chemists would tell me like, well, you need to know the potential surface as exactly and in the entire configuration space as possible. And I would tell them, no, I don't care about the potential surface because the potential energy surface is not an observable. All I care about is being able to predict the outcome of experiments by solving the Schrodinger equation. So whatever enters the Schrodinger equation, which in the form of the potential energy surface, I claim that it should be as good. It should be good enough to allow me to make accurate predictions of the experiments and not better. I don't need my potential energy surface to be extremely accurate in parts of the configuration space that don't matter. Well, so of course, if I change the observable, if I want to look at a different observable, I might need to now repeat my process and reconstruct the potential surface. This way, my potential surface is not going to be, universally applicable. But for the purposes of a particular prediction, I can get my surface this way, and that's all I need.
So
you know
coming back to the previous question, so to put it into perspective, you said that it will always be better when you look at chemical reactions. So you'll always require fewer points if you look at chemical reactions, but that's not entirely true then, right?
Well, again, you know, if my goal is to calculate cumulative reaction probabilities, as in this example, you know, instead of building the potential energy surface based on this number of ab initio calculations, I can get away with this number of ab initio calculations. So then, yeah. So of course the downside is that if I then want to go and calculate something else with that potential energy surface, I cannot be sure that it will be good enough for that other application. So I would have to now maybe add information to that surface that would make it appropriate for the other observable. So yeah,
I'm thinking like somehow this grid-based approach is still very popular, right? Like this method where you acquire many points.
Yeah.
So somehow there be some downside why this Gaussian process-based method is not used all the time.
Yeah, but I don't know why though, because again, you know, if you want to scale this up to bigger systems, right? So I mean, like, you know, very quickly you run out of steam, right? So if you want to calculate surfaces with a very high ab initio level, right? But you know, with these sort of approaches, we can build surfaces that are actually quite accurate for systems that are 50-dimensional, right? And we're going to talk about that tomorrow, I guess, now. And yeah.
Thanks.
So yeah, no problem. Shall I go on?
Just to follow up, so did you try to like take huge systems for which there are no analytical calculations and compare it with experiments?
Yeah.
So like, yeah.
Trying to think if we've done something like this. So normally for these big systems, what we do, we compare our surfaces with what has been done by other people, like the surfaces produced by other people, to show that we can build them very efficiently. I can't think of any example from our work where we looked at an observable that was obtained from the experiment. It is, of course, the next important step. Yeah, I can't give you an example.
Yeah, I have another question. So when you say 50-dimensional surfaces and you have this rule of thumb of between 10 and 100 times the number of points, aren't you making a claim that most chemical systems that are 50-dimensional are only going to need 5,000 points, that this is like somehow the limit of the complexity of their PES?
Yeah, I can make an even better, stronger claim. I will show you results that allow us to, well, that illustrate that we can build a 57-dimensional surface with only 400 points, and that describes the entire complexity. Like I'm talking about the surface for aspirin, for example. I can build a surface for aspirin, you know, using a somewhat different strategy than this, but with only 400 points, and that's going to be accurate to within chemical accuracy globally. So that's basically how efficient those methods are. But yeah, if you want them even more efficient, if you want the spectroscopic accuracy of your surfaces, so then you need to go to more calculations. You will require more calculations, and yeah, so the accuracy of these models is going to increase as well. The error of the models is going to decrease as 1 over the square root of the number of training points. And but the claim I'm going to make is that with a very small number of points, you can describe the surfaces very well, especially if you place those points strategically. But even if you place them at random, you know, like I said, you know, we can build surfaces that are accurate to within 1 kcal per mole for something like aspirin, which is 57 dimensions. but only 400 ab initio calculations. And I'll talk about this tomorrow, and this requires a somewhat different approach, but yeah, we're running out of time now.
Okay, thank you.
So yeah, the purpose of this was just to show the efficiency, how quickly Bayesian optimization converges. And this is another example. So again, in this example, we're looking at reconstructing the polarizability tensor of a molecule, which I believe has 6 independent components in this case, from something like the orientation signal, the time dependence of the molecular orientation, which looks something like the graph in the inset here. And again, you can do this by Bayesian optimization if you calculate the orientation using a quantum dynamics calculation for a polarizability tensor that you take on input as a set of variable parameters. And then you vary the parameters, basically you vary the elements of the polarizability tensor to bring the prediction of the theoretical calculation in line with the experimental observable time dependence of the orientation signal. And so what this figure depicts, this is, I believe, for some molecule like CO2, I don't remember the molecule now, but what it shows is how quickly Bayesian optimization converges. So basically, this band here is, so we start with 20 randomly chosen calculations. And this band of curves here corresponds to different initial conditions, to different choices, initial choices of those 20 calculations. And then you start with those 20 calculations, and then you run Bayesian optimization. And by the time you get to 50 calculations, so in basically just 30 iterations, you're done. So you can see like all of these curves, they converge to the same results. And so then you can read out the polarizability tensor parameters at this point, and they're going to be very close to the experimentally determined ones. So I guess I'm going to conclude, or maybe not just yet, but this plot here shows that the choice of kernel is important for the efficiency of Bayesian optimization. So the different curves here, they basically depict what I was showing in the previous slide, but for different kernels. And as you can see, there's quite a big difference between the dotted curve and the red curve here. And the way we choose the kernels for the red curve is not arbitrary. I'm going to talk about how to choose those kernels tomorrow. It's a specific algorithm that we use. And yeah, like for example, for some of the kernels, you could even get something like this. So that actually doesn't even converge over the number of Bayesian optimization iterations that we considered. Eventually, it will definitely converge, but this particular kernel might require hundreds or thousands of Bayesian optimization iterations. Okay. So again, what we're doing here, we're optimizing a 6-dimensional function, objective function, and each function evaluation is the solution of the Schrödinger equation that takes, in this case, I think, hours of computer time. So yeah, so we want to be able to minimize this with as few iterations as possible, obviously. And as you can see, we can get, like, if we choose the kernel properly, we can get the results with 20 or so iterations. Okay. And, so the strategies are, of course, very general. One other example application that we use this for is to determine the molecule surface scattering matrices in this sort of molecular hyperfine interferometry experiments, run by Gil Alexandrovich in the UK. So what he basically does in those experiments, he prepares molecules in coherent superpositions of hyperfine states, and then passes them through a strong magnet, and that basically separates components of the coherent superposition spatially, and then those components they hit the sample surface, and then they scatter back into another magnet that brings those components back together, and he looks at what comes out of this by the ionization detector. And by doing this, he obtains this sort of the interferometry picture, like the one is in the right upper corner. and then of course, so this picture is somehow determined by what happens as molecules hit the surface. But of course, he doesn't know how the molecular surface scattering affects these sort of interferometry pictures. So one way to deal with this is by treating the scattering matrix elements as variable parameters, and then vary them to bring the theoretical prediction. This is the calculation by Josh Canton, one of my former graduate students, to bring this calculation in line with the experimental results, and that's how you can determine for example, the molecular surface scattering. Okay, yeah, this one came out just a couple of weeks ago. So this is a paper in which we used Bayesian optimization to optimize an organic chemistry synthesis experiment. This is probably my only chemistry paper, but yeah. So what you can see here in this graph that's a little blurry is the function of the yield, the reaction yield, as a function of the number of experiments. Of course, the purpose of Bayesian optimization in this case is to propose the experimental parameters, and there are 4 experimental parameters to the best of my recollection here. And so the purpose is to propose the combination of these 4 parameters that give the highest yield. And so in this particular case, we would start with training Gaussian processes with 10 randomly, or something like even less, like 5 randomly chosen combinations of parameters. And then from there, we would optimize those parameters. And as this graph shows, with as few as 19 experiments, you get the reaction yield that's close to 75 or 80%, which is much higher than anything that was previously achieved for this particular reaction systems. Okay, so I think we are out of time. So what we're going to do next time is talk a little bit more about how Gaussian processes are trained, because this will remind us of what marginal likelihood is, and how it can be used to choose better kernels. And then we're going to see at consequences of a better choice of kernels for some of the more complex problems related to, for example, condensed matter physics work of ours that I will describe tomorrow. So I think this is a good place to end this. So yeah, if you have any questions, I'm happy to stay for as long as you want me to. Thank you.
So thank you. And do we have some questions?
Hi, I'm trying to understand. So you're using these Gaussian processes basically to get an estimate of a function that is very hard to determine, or where the function evaluations are very costly. From the pictures you've shown and from what you were describing, it also looks quite similar to general optimization problems. So is this also used, or could this be also used for general optimization problems for high-dimensional non-convex optimization? Or is there something I'm missing that might prevent you from being successful with this?
No, that's exactly what it could be useful for. I mean, solving general non-convex optimization problems. The problem is, like, if you have a problem for which you can evaluate gradients sufficiently, so the gradient-based approaches will typically work better. So if you know the gradients, say analytically, and this is what you do, for example, when you train neural networks, you can use backpropagation to evaluate gradients, to write down gradients analytically, right? And then that if you have that, if you have gradients, then you can use them to, in a gradient-based optimization, much more efficiently. So your optimization based on gradients will probably be more efficient than Bayesian optimization. But if your function is very expensive to evaluate and you don't have gradients, then Bayesian optimization, I think, is a very good choice.
So when you say you don't have gradients, you mean there's no means of getting the gradient, or it's just too expensive? You were doing, like, for example, in quantum neural networks or variational circuits, you typically don't have access to the gradient. So this could potentially be helpful here, or because you can still kind of estimate it with parameter shift rule, the gradient approach is better.
So 2 of my students are using Bayesian optimization to optimize quantum, circuits and for variational approaches, and that's exactly what it's good for. Yeah, and we're seeing very, very good results. And yeah, so what I'm saying is that in this, like for example, in this case we're looking at, it is very expensive to evaluate gradients. So like in principle, you could do them numerically, right? But then you have to perform hundreds of experiments to evaluate those gradients, and you just can't afford that.
Cool,
And
thanks.
yeah, so Bayesian optimization is also used sometimes for training neural networks, and I've seen a series of papers where they basically claim that they take the human out of the loop when it comes to the process of training neural network, because like when you build a neural network, I mean, like there's a lot of bias that you introduce by designing, for example, the architecture of the neural network and how you choose the activation functions and all that. And this can all be actually optimized with Bayesian optimization, as was shown by some papers in the literature. So that's what Bayesian optimization has been applied with a lot of success to in the machine learning, applications.
I also had a question.
Yeah.
And the approach that you described, you always have now pairs of data which are X and Y basically. If you were in a scenario where the function that you are trying to model were a probability distribution and you only had access to samples of the probability distribution, but not the actual value of the Y's, are there some generalizations that you could do to the approaches that you described in order to make them fit for the scenario?
So a Gaussian process in principle infers a probability distribution, right? And so you have, I hear what you're saying. I have to think about it. I don't think there's a straightforward way. So you want to, you have an arbitrary distribution, and you want to not just you want basically to obtain, to fit the entire distribution, right?
Yeah, exactly.
Mm-hmm. Yeah, I have to think about how one would have to modify this to this problem, and don't have a good answer for you now.
Okay. Thank you.
Okay, so I think that we should go for a coffee. So once more, thank you very much for the exciting lecture, and we are waiting for the last one tomorrow.
Sounds good. I'll see you tomorrow.
Thanks.
Bye now.
Bye. Thank you.